All right, welcome back everyone. Let's move on to Division 7, Chapter 7 in the textbook, which deals with thermal and moisture protection. Like previous topics, we're going to cover this in multiple parts. This one is going to be covered in two parts. This first part, we're going to look at moisture control. How do we damp proof and waterproof our structures? And then also today what we'll be looking at is the thermal considerations. So how do we insulate our structures, exterior insulation, finish systems, things like that. Next time what we'll look at is steep slope roofing, shingles, insulation, panels and siding, commercial roofing, flashing, all those topics. So let's get on with it, starting with this idea like we always do with sustainability in this section, right? So when we look at sustainability of thermal and moisture protection, it really varies on which system. There's so many systems and the manufacturing of each one of these systems and how it's applied and everything else. So you can see this wide list, some good, some bad. So I think that it's kind of a mixed bag. And I think to really look at sustainability, if that's the primary concern during the building process, what really needs to be looked at is which individual products would be chosen or methods should be chosen in order to meet those sustainability considerations. But it's almost like because there's so much to this topic, it's really hard to pinpoint one. But you can read through these and see some advantages and disadvantages to these thermal and moisture protection systems. So let's move on to moisture considerations, damp proofing and waterproofing. We need to control this moisture. Of course, water can exist, or moisture can exist as either a solid, which would be like ice, liquid, which would be like water, or gas, which would be like water vapor. And we tend to think about liquid form, with water. We've talked about this groundwater. We've talked about water running along next to our building. Issues with water penetrating into brick and masonry and wood and swelling and things like that. But we don't talk as much, or we haven't, about the gas form, the vapor form. Now this can be a big issue because when we have it in a vapor form, what can happen is it can condense, meaning there's water in the air and it hits a colder surface and it'll condense and turn into the liquid state, right? And it can also freeze and turn into the solid state. So this condensation, which is when we have the water vapor turning into the liquid state, or freezing turning into the solid state, can happen by a couple different things. One is the migration of water vapor to areas of lower temperature. So if I have a glass of cold water, is probably the classic example, right? And I'm in a humid, warm room, what I'll see is little droplets forming on the outside of the glass, like it's sweating almost, right? But what's happening is the humidity is hitting this colder temperature, changing the physical properties, the phase change of water, turning it into a liquid and then accumulating as water. It can also happen with a temperature drop as well. So that's my dew point type of stuff, right? Moisture problems can occur in these cold climates. If we are in a cold climate with a heated interior, then we can have these moisture problems. It's a differential in temperature. And the same idea if we're in a warm, humid climate and we have an air-conditioned building. So really what it is it's the differences between those temperatures, right? So some considerations we need to think about with this moisture control is that we do have these continuous movement of dimensionally unstable construction materials. So we talked about how wood can expand and contract, right? And we have other dimensionally unstable materials, and that can lead to, in essence, pockets where this moisture can get in and out of. Also, the moisture can cause the dimensional instability, like we talked about primarily with wood, where it absorbs this moisture and expands. And the moisture can cause many issues. It can be chemical issues, like rusting of steel with that oxidation with the iron. And it can have physical changes, such as like the spalling of masonry or concrete, and biological changes. It can increase like this with this wood decay. So in order to control this condensation in our walls, floors, and ceilings, there's really two things we can look at. One is ventilating the spaces. So if we can have an airflow and we can push out this moisture, then it will not be an issue with that vapor condensing. The other thing we can do is provide a sheet or a plastic or a vapor retarder in order to keep the vapor from getting into the structure. So looking more at this ventilation, of course we want to ventilate the walls, crawl spaces, roofs, and ceilings. And within the roofs and ceilings, we want to ventilate with roof louvers or continuous soffit vents, gable end louvers. So this is what we see going on here with these vents underneath. In this case, this is like a soffit vent. And the whole idea is to get air into this attic and then out through this roof, right? Just that continuous airflow. So ventilation, structural spaces dissipate water vapor. That's what I was saying before. This air will remove the water vapor. Should supplement the primary moisture protection vapor retarder. So primarily, what we're relying on is the sheet of plastic, some kind of vapor retarder to keep the vapor entering our structure. However, if we can keep the vapor away from that vapor barrier, we're even better off, right? And ventilation requirements are usually given as a net free area. So you'll hear something like how much venting is needed for what square footage area you're trying to vent. As far as our vapor retarders, like I said earlier, this is your primary method for controlling that moisture, especially true in walls because we really can't vent walls very easily. So that's where you usually see structure, especially with stick framing, and you have this sheet of some kind of vapor retarder right next to the framing. We measure this in this idea of perms. We'll talk about perms in just a bit. And selection generally based on code requirements, and of course those code requirements are based on where we are geographically, because a vapor retarder in Florida would look much different than a vapor retarder in Montana. We can see these different zones for condensation and how one of those tables could be read. So when we talk about this transmission of vapor retarder, there's these three things that can really promote or decrease this vapor transmitting through our retarder, right? The area of the material, cross-sectional area, the thicker the material, then the more it can retard the moisture seeping through. Also, the permeance of the material, or permeability, you may be more familiar with that term. That's what's measured in this idea of perms. So how easy is it for water particles to go through that material? Also, how much force is pushing it through the material? That's your gradient pressure, or differential pressure from one side to the other. Vapor retarders must have 1 perm or less permeance, but more commonly we're looking at 0.5 or less, right? So gives you an idea of what kind of values you'd be looking at. As far as installing our vapor retarders, some things that should be considered is it should be as close as possible to the warm side of the insulation, or warm face of the assembly. So if the inside, if you're in a colder climate and the inside is your warmer space, of course you want the vapor retarder to be closer towards the inside. The reverse is true if you are in a warm environment and you are cooling the inside. The retarder should be as continuous as possible. That should make sense, right? Because if I have a vapor retarder and there's a gap in there, then of course it allows moisture to go through that gap. And it should be installed in a method suitable for the condensation hazard. What kind of condensation are you dealing with? And that may affect the installation. So we have this idea of damp proofing. We talked a little bit about damp proofing when we were talking about CMU walls. But same idea. What it's doing is it prevents material from absorbing adjacent moisture. So if I have moisture directly against my wall, it protects it from it sucking into my wall. Or if it's in my wall, it prevents that moisture from penetrating further. So if I had, say, a CMU wall and I had damp proofing on my inside face, and it's going through the outside, it prevents it from going further in, right? If that makes sense. Typically, some kind of bituminous coating, like it can either be hot applied or cold applied. We'll see those in just a second here. Not suitable, we talked about this with CMU walls, not suitable if water is under hydrostatic pressure. So if your water table rises and you have water, if it's basically immersed in this pool of water, that's not what this damp proofing is about. It's more for a condensation type thing or a flowing water or something where it's a temporary exposure to this water, but not pressure pushing against it. So I said we talk about this hot and cold applied bituminous, and here we can see this is the hot applied. I can see the steam coming off of this surface, right? Typically applied on these underground exteriors, larger job sites. Not used on interiors because we do have this heat issues in transporting it to these interior surfaces, and can be applied either over smooth concrete or the way we've already talked about it is with parging over masonry walls, right? If we're talking about cold applied, we're talking about coal tar or asphalt. Can be used either exterior or interior. However, coal tar is not used as much as interiors because it can be a little stinky, leaves this residual odor, and it can be applied by either with brushes, sprays, or troweling on, right? And here we see a picture of damp proofing of a concrete foundation wall where it's been applied, and you can see it's coated. So you'll see this around. This of course extends down as far down as the wall or into the foundation or into the footing. Now, like we said, now that is that damp proofing is not suitable if you actually have a higher water table or if you have water pressure constantly against your wall. For that, what we use is something called waterproofing. So we can see the difference here where damp proofing, you know, if we have low groundwater, we can damp proof our wall. However, if we're going to have issues with groundwater or water directly against our wall, we want to use waterproofing. I can see this little red line. It's much thicker on the waterproofing side, thicker material, right? And when we talk about waterproofing, now we're talking about a membrane or a coating or a sealer to prevent water from entering, even under that hydrostatic pressure, hydrostatic head, right? 3 different types. We can have membrane, clay, or cementatious. So let's look at those. With a membrane, the membrane, like we see them rolling out here, could be in a sheet. That's what they're rolling out, made out of PVC or EPDM. Or it could be fluid applied. We see them rolling on some kind of fluid. And then we're talking about a polyurethane fluid or hot asphalt, silicone, neoprene. Bituminous, we talked about a little bit of that before. Hot coal tar, hot asphalt, or a combination of those, right? Cementatious, you know about cement when we talked about concrete. Well, we can make in essence, a coating to waterproof our wall made out of Portland cement aggregate and some kind of admixture of acrylic or plastic. Of course, it has to be non-shrinking, because if we have it shrinking, then we'd have cracking, and then we would have a non-waterproof structure. So we need this non-shrinking hydraulic cement. When we're in locations that are hard to reach, sometimes we can use this clay, bentonite clay. The bentonite clay prevents water from going through the material. However, it does absorb that water, so it expands. It can be 10 to 15 times the expansion. When we talked about clay, when we talked about soils and how we can have these expansive soils, same idea, but this is using it as a benefit to suck up that water before it gets to our structure. Like I said, used in hard to apply membrane locations, and it does need room to have that expansion. So the second part of this lecture is this thermal considerations. How are we going to insulate our walls to keep your heat in or keep the heat out and keep your cool air in? Corresponds to book section 7.3 and 7.4. Some terminology. What we're talking about, like I said, is to control that heat gain or loss through the building envelope, which is basically just the exterior of your building. Our terminology, we have this R value, and R value means the resistance of heat flowing through a material. So R, resistance, right? U is thermal transmittance. It's the opposite of R. It's it's the heat flowing through, or how easily heat flows through. So because it's the reciprocal, then I can just find that value by taking 1 over my R value to find my U value. BTUs, British thermal units, that's the way we measure the amount of heat flow. Technically what it is it's the amount of heat required to raise the temperature of 1 pound of liquid water by 1 degree Fahrenheit. But in essence, the way we use it is a measure of the amount of heat flowing as a rate of time. We have 4 types of thermal insulation we're going to discuss: rigid, mineral fiber, loose fill, and then foamed in place insulation. We can see each one has its own R value per 1 inch thick, and there's a variety of values. What I should see is my foamed in, or some of my highest R values, meaning they're most resistant to having heat flow, so most insulating, and these are probably the ones that seem like they're becoming more and more common. And then we have our rigid, or can vary quite a bit in here. We'll talk more about these individually. Loose fill and everything else. So let's start with our rigid insulation. So rigid insulation can consist of many different materials. It could be polystyrene, polyurethane, polyisocyanurate, perlite, phenolic, cellular glass block, organic fiber, glass fiber, and composites. So we have a lot of different materials. Hopefully I pronounced most of them right. But we can see that rigid, meaning it's one solid board, or something that is a rigid, non-flexible type of structure that I can put up against this exterior wall. Polystyrene has this low R value, so that's not good. We want a high R value to be more insulative, right? And deteriorates from light, so we can't have exposed to direct sunlight because it'll start to break down. It's extruded, most resistant to moisture absorption. So where would I use this type of polystyrene insulation? Over structural roof decks, at foundation perimeters, and masonry wall cavities. Remember we talked about those cavity walls before, or masonry structures. That's a good place for it. So it has to be protected from exposure to light, and it's usually in places where we're not looking at high R values, right? Then we have our polyisocyanurate with a foil backing. Now this has a high R value per inch, used for wall sheathing and roof sheathing. If you look up here, we didn't talk too much about this, but there is this reflective aluminum foil, which has its own R value. So what this really is somewhat of a combination, because it has that reflective foil built into it, right? We have our phenolic. This has a much higher R value, and it's better than many of those foams that we were just looking at, used for walls and roofing systems. We have glass, fiberboard. You could have either flat or tapered ends, primarily used for roofing systems. We have mineral fiber insulation. So what this means is interior, the insulation is made from minerals, right? So you imagine breaking down this rock, slag, or glass into small minerals, and that is your insulation. It has resistance to higher temperatures, resistance to fire, moisture, vermin, vermin like the mice and rats, or any other kind of wild animal like a bird that might do damage to your structure, right? So you don't want them burrowing into your walls. Types of products: semi-rigid boards, so 2 foot by 4 foot, 1 to 3 inches thick, used in curtain walls. That's our exterior wall insulation. Semi-rigid means that you can flex them. So when we were talking about rigid just a second ago, if I try and flex one of those rigid insulation boards, it would just snap in two. Semi-rigid means that I can flex them a little bit, but they aren't totally flexible, right? So some types of products: we can either have bats or blankets. What's the difference between a bat and a blanket? A bat is like 4 foot long, versus a blanket is like a long roll that we can roll out and cut to whatever length we need. Craft faced. So what is craft faced? It's like a paper, almost like a thin cardboard type paper that goes on the outside of it. And some of these can be faced and some are not faced. If it is a friction fit, that means it doesn't necessarily need to be faced. So what does friction fit mean? That means that I could take this fiber and put it in between my studs, and the friction, it fits close enough where it will not come back out. That's a friction face. versus if it's craft faced and I have this paper, the paper's slightly longer and I can tack it to my 2x, locking it into place. So that's really the difference between a craft faced and a friction fit unfaced. And with these mineral fiber boards, you could have either one. Used in walls, partitions, below floors, in crawl space, above ceilings and attic. So a third, loose fill insulation. We see a picture here. It's like this blown in stuff, right? You see in attics more than anywhere else. It's made of fibers, granules, chips. It's not free flowing, should not be used in walls or other closed cavities. Basically what that means is if I was trying to blow it down some walls, what happens is it won't flow into all those cavities and I could have an air pocket, right, where I don't have any insulation. So either pouring or blowing of wool includes slag and glass wool products, moisture and vermin resistant, typically used in attic spaces. That's the place I most likely think of it. Two different characteristics, vermiculite and perlite, and these can be put into the masonry cavities. Remember these masonry cavities we talked about last time, like CMU walls, right? And they are moisture and vermin resistant and non-combustible. So more insulation, a way to insulate our CMU walls directly. We also have our fourth type, foamed in-place insulation, which is made out of either a polyurethane or a polyisocyanurate or phenolic-based materials. So basically this is like the thin spray-in material. I think there's a picture. Here's a picture right here. You're spraying it against your wall and it's really thin and then it just expands, and it takes a while to expand, and once it expands then it can be shaved off so it's level with these 2x, giving you a solid filled cavity core. And here it says it expands to 30 times its initial volume, but it takes time for it to cure, for it to expand. Really nasty stuff when it's wet, but after it's solid it's really nice to work with. And it solidifies into this cellular plastic. Other insulation materials, we could have fiberboard. Fiberboard, this is a picture of fiberboard right here. It's more used in temporary buildings, so it's not something that we consider to be a long-term solution. It's very fragile, soft, damages easily. If you bend it at all, it just breaks apart on you. It doesn't have the highest R value either, but it's very inexpensive, and if you need like a shed or something like that, and you need a temporary insulated structure, you could use fiberboard for something like that. We also have reflective. I mentioned reflective a little bit earlier, how it's placed on the surface of some of these other foam boards. Well, it can be its own insulating property itself, but you need this air space in order for it to really be effective. So that's in essence what's happening with the foam, is you're relying on the air within the foam and that reflective to reflect back the heat that is hitting your insulated layer. And here's a quick summary of the standards involved, the ASTM standards for each type of material, from polystyrene down to your mineral fiber, and you could look at all of that and even go back and look at the standards if you really wanted to. So as far as the installation of the insulation, if we were looking at slabs on grade, the heat loss is primarily through the perimeter walls, meaning see how I have this thick insulation on the edge of my slab on grade, but I'm not really so concerned about the stuff that is vertically pushing down against the soil, because I really don't have as much heat loss there. The majority of heat loss is around that perimeter of the wall, so that's the part that really gets the insulation. Of course, it should be non-absorptive of moisture, because if you are underground, then you're going to have water that is filtering through your soil and coming up in contact with that rigid insulation, and the last thing you want to do is have that either start to decay your insulation or absorb into your insulation. So this is the decaying part, right? It shouldn't be damaged by the wetting, so it shouldn't absorb in there, so just brush on down. Insulation should be sufficiently rigid to resist damage during placement of concrete slab. Makes sense. So if I'm pouring this slab and it's bumping up against the insulation, we can't have it, in essence, either crushing or in some other way getting damaged by that concrete. Resistance to decay and insect damage, at least 1 inch thick, but thicker is better. So if you could do 2 inches, get more insulation. Mostly this is a polystyrene product, but sometimes a glass fiber or other plastic foam boards. And here I see it in place with this slab on grade and my insulation around the outside. Of course, that goes down into the soil as well. I'm just seeing the little top part of it, right? Crawl spaces and floors, we can reduce that heat by insulating the walls of the crawl space. If we aren't going to heat our crawl space, then of course we should heat the underside of our floor between those floor joists, because we'd have, otherwise that cold air would be coming right up through our floor. Not only is it uncomfortable to walk on, but you'll lose a lot of heat for your entire structure that way as well. And what I see is a flexible insulation. So we talked about flexible, non-flexible, or we talked about semi-flexible. This is absolutely flexible, meaning I can bend it around to get it into these cavities. Right here I'm going next to this header joist and whatever else I need to insulate, right? But regardless, in both cases, what we need is this vapor retarder, and that should be facing the living space. So if you think about if you're in a crawl space and you had your wood studs, then you put your insulation in between those studs, and then right above that is where you're putting your vapor retarder. For walls, we could use either rigid or this batt insulation. So here we see some rigid, here we see some batt insulation. Depending on what kind of R value is needed, I get a much better R value with this insulation than I do with this foam insulation. So for masonry walls, we have some of these same products we talked about before, and we can also have something filled into the cavities, which we've also talked about before. As far as this vapor retarder, once again, it's facing the living area. So my vapor retarder would go right on top of those studs, encapsulating that insulation and keeping the vapor from coming either from the outside in or the inside out. Ceilings and roofs, we want to use this flexible insulation. Once again, it can mold around. I can see this flexible going around this little cathedral ceiling here. Vapor retarder should also be used, and once again, next to that living space, we see a reoccurring theme here. Check code for vapor retarder requirements. May use batt or blown type of insulation, and use baffles, channel vents in the eaves to ensure airflow. So once again, we want the air to be able to flow through your building, and here we can see this guy is blowing in this insulation, right? Well, see up here what we have is, it looks like, I don't know what that is, but it looks like it may be wood or something else, almost like a, but what it is it prevents this blown insulation from going in between these two buys and then going down into the soffit and blocking my vents, and then I wouldn't be able to have airflow. So that's why he's doing this, to make sure this airflow continues along here. This is another product which would ensure that airflow would continue along here. But any way that you're not going to plug up those channel vents when you're doing your insulation. So we also have this exterior insulated finish systems, EIFS. How this is pronounced is EIFS. And it's also called a synthetic stucco because it looks like stucco when you apply it. It's non-load bearing. It's this texture put on the outside. It provides this continuous insulation of a building envelope. So it's an exterior insulation, and what it's built up from is we have a protective finish. So this is going from the outside in. We have the outside, we have a protective finish, then we have our base coat, then we have our insulation, then we have our sheathing, and finally we have our sheathing is attached to our furring or framing. There's two different types of EIFSs, or is it just EIFS? I'm not sure. There's either polymer based or polymer modified, so PB or PM. And here's a comparison between those. For the PB, for the polymer based, it is going to be more of a softer finish coat versus the polymer modified would be a hard coat, a rigid structure. As far as that base coat, which is right inside from the finish coat, our polymer based is much thinner. See, it's 1/16 of an inch. That's tiny, versus or up to a 1/4 inch, versus our polymer modified starts at a 1/4 and goes up to almost 1/2 inch, right? Because of that affects what kind of reinforcing we can have on that base coat. It has to be just fibers within this really thin material on our polymer base, so we have a glass fiber mesh, versus our thicker polymer modified, we can use a wire lath or glass fiber mesh, something a little thicker, right? Then we have our insulation, pretty similar. This one is a less expensive. This is a more expensive for our polymer modified. We have our sheathing. That's the same in both of them. And cracking considerations. With our polymer modified, we do require control joints because it is more of a rigid structure. It can't move. That means that when it tries to expand or contract or whatever else is going on with movement, it'll start cracking. Because of that, we control that by adding control joints. Quick slide just showing the difference between PB and PM, and you could look at that, but we've basically discussed it. Little difference on attachments, where this is using some kind of clip or this is using an adhesive, but other than that, just a cool image of what it looks like for our different layers, right? Finish coat, base coat, some kind of reinforcing mesh for one, for a thicker one. We have our board, our insulation board, and then our vapor retarder, which we talked about, and then our gypsum sheathing right against there. So some characteristics of this EIFS. What the reason we could have failures, it could be that you didn't consider you didn't recognize all of the characteristics of the environment to match up the right type. We'll talk more about those in the next slide. Protective coating is vapor permeable, but permeability reduces when more reinforcing is added. Prevent condensation, which can cause separation of layers, so it definitely is not a vapor barrier in and of itself. It needs that vapor barrier, otherwise your layers could separate. And EIFS system should always have a complete vapor retarder. This is building more on that idea to keep that vapor out of there. So when we are selecting, what do we want to consider? The weathering characteristics of the system, meaning how will weathering affect the overall product, right? How will it start to degrade with different types of weathering and its effects? Wind-driven rain resistance, resistance to salt spray, absorption and freeze resistance. If water does get in there and freezes, how resistant is that to falling apart there? Mildew resistance, water vapor transmission, impact resistance, negative wind load performance. Negative wind load means that from Bernoulli, if you studied that fluid flow, if I have wind against a surface, it creates a negative pressure, meaning it's pulling it apart. So negative wind load means that it could be trying to pull apart the layers. So on a high wind load location like Wyoming, that'd be a bigger issue, right? So that's what I have on this part one, and hope you found that informative. As always, let me know if you have any questions or comments, and I'll talk to y'all later. Thanks.